Guten Tag and welcome. Today we're going to do irrotational flow. We're going to continue in our series, and today we're going to do my favorite flow, or one of my favorite, the Rankine half body. You know, up to this point, really, we've just been doing a lot of preliminaries. We defined what a streamline is. We defined what a potential function is. We derived the Laplace equations, the boundary conditions. We went through some solutions, the building blocks, and all of that. And today we're finally going to do some fluid mechanics. And so the Rankine half body is a problem that kind of encompasses the whole picture. So it's a nice one to look at. So the objectives is to use the basic flow solutions, namely uniform flow and a point source, to build a more complicated flow. We've already done the doublet. We did that last time, which was combining a source and a sink. And today we're going to do the Rankine half body. That's a free stream and a source. And the next time we'll do the Rankine full body, or just the Rankine body, which is a free stream and a doublet. Here's our hero. Here's William Rankine. He was born and lived in Scotland, and he taught at the University of Edinburgh. And he's quite a famous fluid mechanics and a scientist. He not only developed this flow field and so forth, but is also known as for the Rankine cycle, of course, in thermodynamics. So quite a giant within the world of thermofluid sciences. All right, so here is the Rankine body, and I've shown this picture a few times before. It's essentially a bluff-nosed body here that has been submerged into a flow field. And you can see that there are bubbles that are illuminating what the flow field looks like, kind of these streamlines here going over the flow field. And this was done in a water tunnel with air bubbles, probably a hydrogen bubble technique, and I included a reference. And the hydrogen bubble technique is kind of interesting. If you wanted to make these tiny bubbles, what you do is you could take the element out of a toaster and you could submerge it in water, and when you apply a voltage to it, it can disassociate the oxygen and the hydrogen from the water and provide the gases, the oxygen and hydrogen gases, that then form these tiny bubbles. So if you want to try this out at home, you can just bring a toaster with you next time you take a bath, and you could see these bubbles. I'm just kidding. Don't do that. But that's basically how it works. The Rankine half body extends out to infinity here. So that's why it's known as a half body, right? Because we're assuming that the body extends out to infinity in the positive x direction. We superimpose the free stream and a point source in order to construct the Rankine half body. The resulting solution, the streamlines, would look something like this. I apologize for this white block here that appears in my solution, but that's basically what it looks like. We have streamlines that represent the body, and then streamlines that go over the body. Let me separate them out so you can see them. Now, I think that something that's important to keep in mind is that this is the flow solution that we get from the irrotational flow solution, right? And so it looks like you got these streamlines, and they look something like these streamlines here, and that's all great. But what about what's going on inside the body? Well, remember, this whole thing is the flow solution for the free stream plus a point source. So maybe you're not doing the Rankine half body, but instead you're doing a problem where you're looking at maybe a river, and then you have a pipe, and you're injecting flow into the bottom of the river, so it's emitting this flow like a point source, and the river is combining, and you're looking at where, how far downstream this emitted flow is combining with the river water, kind of on an average sense. So from this one solution, we can think of several different solutions that would represent physical phenomena. So what we're doing here is we're picking this streamline, which we're going to call the stagnation streamline, to represent the body, and then we're thinking about the flow going on outside of it. We could pick this streamline that represents some other body and think about what the flow would be inside. We could think about combining them all together. You know, we could pick this streamline right here and think of that as a bump, and flow goes over this bump like that. So any streamline can represent a solid surface. That's the point here. All right. So in order to construct the Rankine half-body, we just sum up the free stream velocity with the point source, and I've written it here in xy coordinates or in r theta coordinates. And as we move through this solution, you'll see it's convenient to switch back and forth between the Cartesian coordinate system and the cylindrical coordinate system, r theta. All right. Once we have this side, this streamline, we can ask some really basic questions like, what's the standoff distance between the origin, the xy origin, and the leading edge of the Rankine half-body? That leading edge, of course, is the stagnation point for the flow field, so we call that the stagnation point and denote it with this S. So really this question is, what's the standoff distance between the origin and stagnation? What's the value of the stagnation streamline? So it's not necessarily true that this streamline is going to have a value of 0. We're going to have to calculate it and find out what it is. And I've used the word saddle here because that's a word from mathematical morphology, right? Manifold theory. When two streamlines come together and intersect at a point, and then they emit away from that point is called a saddle. And so the value of the stagnation streamline is the streamline that passes through stagnation and the saddle point, right? What's the thickness of the body far downstream? So what is this H max far downstream? So between A and H max, it would help us define any body shape that we wanted to, right, if we were investigating a particular nose shape. And then what's the pressure distribution along the body? If we want to know what the forces are, the fluid dynamic forces on the body, at least the inviscid forces, we would need to know what the pressure along the body is. So these are great questions to ask, and let's run through the solution to these. All right, so in order to locate the stagnation point x and y, we need to first determine what the velocity field is, and then we'll set that velocity field equal to 0 and then solve for the xy location where that is 0. Is that stagnation point the only point in the flow where the velocity is 0? I think it is, right? So we won't have any problems with multiple solutions for x and y equal, for u and v equal to 0. So here's my streamline, my stream function. That's the general stream function. It describes the whole flow field. And in order to determine the velocity, we just take the gradient with respect to y, that'll be our scalar u velocity, and take the gradient with respect to x, and that'll be our minus scalar v velocity. And so I just plug those in and plug in my stream function and operate on it. And I'm going to do that via Maple. And then I'm going to set it equal to 0. Now, I am going to do a little tutorial in Maple because it's such a helpful tool. If you haven't seen or don't know how to use Maple, then have a look at the tutorial. I'll run through some basic plotting and how to take derivatives and solve simple equations. And if you haven't seen it, I think it'll really help you out. All right, so we've set these equal to 0. And then we have two equations. And we have two unknowns, x and y. So we just solve for them. So the stagnation point, A of x comma y, is equal to negative the flow rate per unit length. That's the flow rate of the point source per unit length, divided by 2 pi u, the source, the velocity strength. So it makes sense that the standoff distance for the stagnation point would be some function of both the strength of the source and the strength of the free stream. We could also describe the location, the stagnation location, in r theta coordinates, and I'll let you try that yourself in r theta coordinates. Just repeat this procedure in r theta coordinates and see how that works out. All right, so now we can determine the standoff or the stagnation location. Or we just determined the stagnation location. And so to determine, the next question was to determine the stagnation streamline. So the stagnation streamline is the streamline that passes through this stagnation point. So we just take the stream function, here it is, and we insert the stagnation point, right? So we just plug in here theta is equal to pi, and r is equal to this amplitude, and it's simple enough to do that. Sine pi is 0, and so we're left just with this this term v dot divided by L, so the source strength by 2. So it's not 0. The stagnation streamline is not 0 in this case, but it is related to the strength of the source. And so recall that everywhere along this line, the stagnation line, the value of the stream function is this v dot by L. All right, so determine the thickness H max far downstream. Well, what we want to do is go far downstream. So it seems like the easiest thing to do is what's the y location of the stagnation streamline as x goes to infinity. So I can set up this limit. I'm saying here's the stagnation streamline. Let x go to infinity, and then let y go to h, and that would be our height above the x-axis. So I'll take the limit as y goes to infinity, and as x goes to infinity. And so when x goes to infinity, h over infinity goes to 0. The arctangent of 0 is 0, so this whole term drops out, and we're left just with this UH. So we would set this UH value equal to the value of our stagnation streamline that we solved on the previous slide, and then just solve for H. So H max is equal, again, to the balance of the strength of the point source, V dot by L, and the free stream U. That makes a lot of sense. What's the pressure distribution along the body? Well, that's a really good aerodynamic question. And the way that we're going to get it is we're going to use Bernoulli equation. But before we use the Bernoulli equation, I think it would be nice to look at the derivation of the coefficient of pressure. So instead of solving for pressure directly, let's solve for the coefficient of pressure. Let's see here. We could do this a couple of ways. One way is we could think of combining this hydrostatic pressure and the thermodynamic pressure together as a single term. Or we could neglect the change in hydrostatic pressure from the center line to the stagnation streamline. Recall what the Bernoulli equation is. It's the balance between the internal energy, or the pressure, plus the dynamic pressure, 1/2 rho U infinity squared, and the hydrodynamic pressure. So it's really an energy balance. It's internal energy, potential energy, and kinetic energy. And we have these various terms: thermodynamic pressure, dynamic pressure, and hydrostatic pressure. And the left-hand side of this equation here represents the far field. So this is what the pressure and the velocity and the elevation head are far away from the action, right? Back far away where the free stream is just the horizontal free stream. And it's equal to, the sum of these three is equal to the change in the pressure, in this case along this body, plus the dynamic pressure, which would be also a function of the shape of the body, and then the change in hydrostatic pressure. So these three are equal to those three. And you remember how this goes from your undergraduate fluid mechanics. We typically neglect this hydrostatic pressure, and then we see that we have this inverse relationship with pressure. As the pressure goes up, the velocity's got to go down, or vice versa. The velocity goes up, the pressure goes down. All right, that's enough on that. Let's calculate what the what the coefficient of pressure is. And we'll proceed by dividing through by this constant dynamic pressure. It's constant because we're far away and we're assuming that U infinity is equal to a constant. So we divide every term by this constant. So we get this plus 1 equals the local pressure divided by the far field dynamic pressure, the local dynamic pressure divided by the far field dynamic pressure. And we rearrange that into pressure minus pressure. So I move the pressures to the left-hand side, and I move this 1 over to the right-hand side. And I get this expression here. And I recognize that this is dimensionless, right? That pressure minus pressure divided by the dynamic pressure would be unitless. And then the right-hand side is quite useful. We just get 1 minus the velocity squared over the far field velocity squared. And sometimes that's written as Q. It's just the magnitude, right? So it's the scalar sum of the velocity vector components. So this is quite a useful definition, this guy right here, because it just involves velocity, and then from that we get the coefficient of pressure right away, which is much more really convenient to work with than the actual pressure with units in it. Okay. So you can see that this coefficient of pressure for any velocity is going to be equal to something less than 1, right? If the velocity is 0, we would get a coefficient of pressure of 1. That makes a lot of sense. If the velocity is 0, we're at the stagnation location, and we're all of the, here, we're at this instance where this has gone to 0, and so the far field pressure plus the dynamic pressure, that's the maximum pressure we can get here, is equal to the local pressure. And then as the velocity increases from stagnation, one would expect that as the velocity increases, the pressure decreases. And so the pressure could decrease all the way to U, Q goes to U, that would be 0, right? So we expect C sub P to vary between 1 and 0. That makes a lot of sense. All right. So in order to calculate what the coefficient of pressure is over the Rankine body, we can use Bernoulli equation to do that. But first we need to know what the velocity along the body is. And to know what the velocity along the body is, we would need to know what the position along the body is, right? We need to define the body shape. And then we could insert that into our velocity equations, and then we could insert the velocity into our coefficient of pressure. So the first thing to do is calculate what is the position of the body. In other words, we could do this in x and y coordinates, or we could do it in r theta coordinates. I think it's easier to do this in r theta coordinates for some reason. So let's look at this cylindrical coordinate system definition of the stagnation streamline as I've written here, and let's just solve for r, right? So we know what the stagnation streamline is. It's this value. This is the definition of what the streamline is. So I can rearrange this equation for r, and I get this expression here. So this little picture here is showing you what I'm talking about. Here's the kind of the Rankine body. That's the stagnation streamline. And this is really showing what's the amplitude of r, or the magnitude of r, as a function of theta, as theta varies from 0 to pi. Does this make sense? Well, what would you expect the value of r to be when theta is equal to 0? Well, it looks like r would have to go to infinity, right? If this is the Rankine half body and that body extends to infinity, then r should go to infinity as theta goes to 0. Is that what happens in our expression? Let's see here. If theta goes to 0, then this goes to 0. That's fine. 1 minus 0. And then, I see here, if theta goes to 0, sine theta goes to 0. So that's, and this is a constant in the numerator, so that's something, a constant over 0. That does, in fact, asymptote to infinity. What about if theta goes to pi? What would you expect r to go to? Well, it should go to the amplitude of the stagnation point, right? And we solved for that. That was question 1, I think. What is the location of the stagnation point. So let's try it out. Let's see, if I put in pi here, I get theta over pi, which is 1, 1 minus 1 is 0, and then in the denominator I get this sine theta that's going to 0. So I'm getting 0 over 0, of course. I need to use L'Hopital's rule. So what is that? That's where you take the derivative of the numerator and the denominator with respect to the guilty variable, theta in this case, and then we'll take the limit again. So if I take the derivative of the numerator, it's quite easy to take that derivative. I'm just going to get v dot pi over L, and the derivative of sine theta is cosine theta. So I get something that looks like that. Now this looks more well-behaved. I'm just going to get pi for theta in the numerator, and cosine of pi is 1. So yeah, this is nice. It converges. My pi's are going to cancel. I just get v dot over L, or the magnitude of the point source, divided by 2u, the free stream velocity times 2. And this is, in fact, if you look back, the value that we got for the stagnation point. So that makes a lot of sense. I think we got the right equation here. All right, so we need to solve for what the velocity is along the body. And first, we need to decide what the velocity is everywhere in the flow field. So we can do that using the definition of the streamlines, and I'm going to work in cylindrical coordinates. So let's see here. The radial velocity is equal to 1 over r times the derivative of psi with respect to theta. And I can just plug in what my definition of the streamline here is and take that derivative. And likewise, the velocity in the theta direction is equal to minus the derivative of psi with respect to r, and that's quite easy to do. So these are the velocity components, u of r and u of theta, everywhere in space, right? Not just on the body. This describes the entire flow field. So we can form our velocity magnitude vector, just the magnitude, by taking the vector components. So q squared is defined as u of r squared plus u of theta squared. And I got all those terms, so I can shove them in there and square this and simplify it down a little bit. So I get this expression here for how the magnitude changes with respect to r and theta. And I can insert this into Bernoulli equation. This, however, is the flow field everywhere, right? So we need to then put in the location of the body. So that's where that's why we derive this expression here. We need to know what the position along the body is, so we can do that. And we know what the position along the body is, so we put this in for r, and we get this simpler expression. So this is the coefficient of pressure everywhere in the flow field that we derived in the previous page, where A is equal to our standoff distance. And now, when we insert the description of where our stagnation streamline is, the relationship between r and theta, we get then what's the coefficient of pressure just on the streamline itself. So this is a very famous relationship that the coefficient of pressure along the Rankine half body is sine squared theta over pi minus theta squared minus sine squared theta over pi minus theta. All right. So here it is. Now let's check the asymptotic behavior of this solution. What would you expect the pressure far downstream to be? Well, let's think. I can calculate this. If I let theta go to 0, this is far, far downstream, I would just take the asymptotic limit of our coefficient of pressure as theta goes to 0, and I get sine squared is 0, and sine 2, 0 is 0, and then the bottom doesn't go to 0, it stays as pi. So really, this becomes 0, right? The coefficient of pressure far downstream is 0. Now we know that the coefficient of pressure, C sub p, it varies. here's our expression for it. It varies between 1 and 0. And really what it means, if the coefficient of pressure is equal to 0, it means that the pressure is equal to, right, P infinity. So far, far downstream, the pressure along the body recovers to P infinity. That makes a lot of sense, actually, doesn't it? All right. At stagnation, what would you expect the pressure to be? Well, again, looking at this expression, at stagnation, Q goes to 0, so I would expect C sub P to be 1. The maximum pressure would be at stagnation. But in fact, when I plug it in, I get that pi goes, or theta goes to pi. I get this sine theta is going to go to 0, and that's going to go to 0, and pi minus pi, that's 0, 0, 0. That's again 0 over 0, which is undefined, so we'll take the derivative again with respect to theta, and try it again. And you can see that the sines all turn into cosines, and then this theta just kind of drops out, so we end up with something that doesn't go to 0, but rather it goes to 1, and that is quite nice indeed. So that is what we would expect. The coefficient of pressure goes to 1 at stagnation, of course. So what does the pressure field look like? Well, we can plot this as a function of theta, and it has the characteristics that we thought. It's kind of interesting. It doesn't just go from 1 to 0. It actually starts off at the maximum pressure at the location of stagnation. And again, that's where all of the dynamic pressure has been given up to the thermodynamic pressure. So the total pressure at the leading edge is maximum. That's 1. And then as the velocity increases from 0, the pressure must decrease, right? So it decreases, decreases, decreases. It decreases down through 0, actually, and goes negative. So it goes negative. What does that mean? Well, if it's negative pressure, it means it's just below P infinity, whatever that is, right? So below the atmospheric pressure. It reaches some minimum pressure, and then it slowly recovers as it moves up over and around the body. So we can calculate easily where it goes through 0. That's about theta of 113, so it's not quite past 90 degrees, and then it begins to asymptotically increase to 0. So this would represent pressure above P infinity, or positive pressure. This region here represents negative pressure, or below the reference pressure, which is P infinity. So sometimes you'll see it plotted like this, and this is kind of a nice plot. This is supposed to represent the pressure. The Rankine body is like, like this here. And so you can see that the pressure is positive above atmospheric pressure, then it goes through. This location here would be a pressure of P infinity, and then it becomes below P infinity, and then slowly recovers asymptotically back to 0, or P infinity there. So that's kind of a nice plot. All right, so in summary, we derived or just superimposed the free stream and the point source and got the basic stream function for the flow field. We then calculated what the body shape is for the Rankine body, the Rankine half body, I should say. We then solved what the velocity field is everywhere in the flow, and actually that's good for inside the Rankine body if you wanted to know what it is. And then we determine what the pressure coefficient is along the stagnation streamline, which defines the shape of the Rankine half body. And then along the way, we solve for what these various parameters are that define the shape of the Rankine half body. Basically, the thickness above, the thickness of the body, and its standoff from stagnation. All right, so that's the Rankine half body. We went through that problem. We've already done the doublet, and we've covered the Rankine half body. So the next one we're going to do in this series is the Rankine full body. And that's essentially uniform flow over a circular cylinder, where the circular cylinder is the doublet. So we will take that up next time. All right. So until then, try out some of those things that I suggested in the lecture that you do, and we'll see you again next time. All right.